Well, hello there, Cape Chemistry Unit 2 student. Welcome back to another video. And in this video in particular, we will be helping you with your paper 1 examination preparation. And to do so, we'll be working through the specimen paper from 2017 that Cape provided us with, okay? Okay, so moving along, you know the drill as usual. There'll be 45 items and you will have an hour and 30 minutes to answer all of them. So that gives you roughly 2 minutes per question, okay? Okay, so moving right along, let's look at question 1. Question 1 says, which of the following may be responsible for the wide diversity of organic compounds, right? So whenever we see a question like this, immediately we're thinking, what is it about carbon that makes it particularly, able to give us this wide array of compounds that we see in organic chemistry? And is it that, 1, carbon forms strong bonds with itself? Yes, that's correct. We call that catenation, right? Is it that carbon forms 4 bonds? That's correct. That's tetravalency, right? Is it that carbon exists in 3 allotropic forms? Not particularly. That's not particularly useful in organic chemistry. Is it that carbon acquires a full octet of electrons? Not particularly. That's not the reason why we have this diversity, right? The reason is because carbon forms strong bonds with itself, so that's catenation. It forms 4 bonds, that's tetravalency. And then no hybridization and resonance or other properties of carbon that makes it particularly useful or gives rise to this wide diversity of organic compounds, okay? All right, so the answer here then will be A. So 1 is A, okay? All right, so moving along to question 2. Question 2 says, which of the following is the structure of 2-phenyl butanoic acid? Okay, so we're looking for a structure that has 4 carbons, right? It has the COOH group because it's an acid, it's a carboxylic acid, and we're looking for a phenyl ring on the second carbon, okay? So let's see, 4 carbons, 1, 2, 3, 4. And on the second one, there's a phenyl ring here. So perhaps A could be our answer, right? So A is in fact our answer here. So we see 1, 2, 3, 4. So that's a butanoic acid. And we see that on the, let's count from here, right? 1, 2, 3, 4. So 1 on the second carbon, we see that we have that phenyl ring, and we see that we have 4 carbons in a chain, so that's butanoic acid, and then the carboxylic group tells us that it's an acid, okay? So our answer for 2 is A. So moving along to question 3 now. Question 3 says, which of the following compounds can be resolved into optical isomers? So what's an optical isomers, guys? It's when there are 4 different groups attached to the central carbon, right? So if we look at all these different structures, we'll see that whatever we pick as our central carbon. So say we look at this carbon, we see that there's a H attached to one side, and then there are 2 methyl groups. So that's not gonna work, right? And similarly, if we look at this carbon, we see that there's a H on one side, a H on one side, a OH on one side, and then a carbon. So the 2 H's makes it so that this one wouldn't be an optical isomer, right? Let's look at this one. Or this carbon here is an amine group attached, but it also has 2 hydrogens, right? So that's not optical. Let's look at this one. This one is CH, and then there's an amine group, and then there's a methyl group, and then there's a carboxylic acid group. So this one looks like it could be our optical isomer, right? So C is our answer here. So remember, when we talk about optical isomerism, we're talking about a situation in which there are 4 different groups attached to a central carbon. So C would be our answer here, okay? All right, so question 4 says, which of the following features may be characteristic of condensation polymers? So we know that when we have condensation polymers, we have 2 groups that condense together to form that polymer, okay? And they give off a small side molecule, right? So which of the following features may be characteristic of a condensation polymer? Presence of OH and COOH groups in monomers. Yes, this could work because those can condense together to give us an ester, right? So that would work. Do we have the elimination of a small molecule? Always. We'll always have that in condensation polymers. Region of unsaturation in monomers? No, that's not true. Because if it was unsaturated, then we wouldn't have gotten a condensation polymer, right? We would have gotten an addition polymer. Okay, so the answer here is 1 and 2, and so our answer will be C. So the answer for 4 is C. Okay. All right, so moving along to question 5 now. Question 5 says, Kiana is a polymer that feels like silk and has the following generalized partial structure. So we're looking at our partial structure here, and what we see immediately is that there's an amide linkage, right? Where we have that NH and that C double bond O. So that's an amide linkage. And what that means is that this polymer was formed from the condensation of a diacid, right? There was a diacid that reacted with a diamine, and that's how we got that amide structure there that we see, right? So there's a diacid and a diamine that reacted, okay? So they're asking us the pair of monomers in Kiana. What were the two monomers that gave us this polymer, okay? So remember now, we're looking for a diacid and a diamine, right? And particularly, the diamine portion is supposed to have in this Y, right? Because you see that that's sandwiched between the NHs, right? And then the diacid should have X in its monomer. And so this should be in our diacid. So we're going to look for something that has that, okay? So we see that this is a diacid that has X in the center of it. And we see that this is a diamine, which has Y in the center of it, as shown here. And so this is our answer, okay? So our answer for 5 is A. And remember, we're just breaking down the amine into its monomers, and we know that we have to get a diacid and a diamine, and we know what these connection points should be based on how they appear in the repeating unit, okay? So A is our answer there. And then moving along to question 6. Question 6 says, which of the following represent naturally occurring macromolecules? So we're looking for macromolecules that are found in nature that we didn't synthesize in a lab, right? It's just found naturally. And so the very first one that we look at here, we see that this is nylon 6,6, and that's a synthetic polymer. So that's not natural at all. So we strike out this one. Let's look at this one now. This one looks to be what? This one looks to be an amino acid of some sort. And in the one case, this amino acid has a methyl group as a side chain. And in this case, this one has like an alcohol as a side chain. So this is an amino acid, and those are naturally occurring. So that could work, right? And when we look at this one, we see that this looks to be a polysaccharide of some sorts. And we know that polysaccharides are naturally occurring. So that could work as well, right? And we look down here, what's this one? This looks like a phenyl ester of some sort. You see that COO, that's characteristic of an ester. And this looks like one that's synthetic, right? A synthetic ester. So we're not going to choose that one, okay? So the naturally occurring ones from these structures is 2 and 3. So let's look for that among our answers, and we see that that's B. Okay, so our answer here for question 6 is B. And we're moving along to question 7. Question 7 says, to which carbon atom in the compound below will an electrophile be attached? Okay, so electrophiles are electron-loving, so they're gonna want to attach themselves where there's an electron-rich carbon, okay? So what we're looking for in this molecule here, in this compound, is we're looking for the most electron-rich carbon, okay? No, this carbon here won't be electron rich, right? This carbon here won't be electron rich because it's actually attached to directly to the phenyl ring, which is electron withdrawing, right? So it will end up being that this carbon here actually has a partial positive charge. So we rule out this one. It's not A. Let's look at D. If we look at D, right, this carbon here has this carbonyl group attached here, which is electron withdrawing. So it will be pulling electrons to itself, making this carbon having a partial positive charge. So it's not going to be that one either, right? And if we look at this carbon here, we see that that's a carbonyl carbon. So that's going to have a partial positive charge on it, right? While this oxygen is negative. right? And so this is not the one. And so what remains is B. And if we look at B, we see that B is this carbon here that's in that phenyl ring. And of course, we know that the phenyl ring itself is very electron rich, right? And so if this carbon is within the ring, then the electrophile will want to go and attach itself there more than any of the other ones, okay? So the answer for 7 is then B, okay? So just think of what electrophile is. It's something that loves negative charge. And so look for the carbon that would have the strongest negative charge. And that's where the electrophile will want to go. Okay? Okay, so moving on to question 8. Question 8 says chlorine reacts with methane to form chloromethane. The organic intermediate in the reaction is it an ion, is it an electrophile, is it a nucleophile, or is it a free radical? Now, the way that we approach this one is that we know that when chlorine and methane reacts, right, that's a free radical substitution. That's the mechanism of that reaction. And within that, there are free radicals that are formed that kind of allow that reaction to continue, right, to go on and on. And so, of course, our intermediate then would be a free radical, right, because this is a free radical substitution reaction. So there are free radicals that would be at play there, okay? So our answer for 8 is D. So moving along now to question 9. Question 9 says compounds X, Y, and Z below their isomers, right? These are all isomers. So they're asking us now the order of decreasing ease of removal of the bromide ion by hydrolysis is, all right? So we're going to add water, and then which one of these is going to be the easiest to remove the bromide ion from? And they want us to show the order of decreasing ease, right? So where will it be easiest to remove it from? And then where will it be the hardest to remove it from? So we have to look at the group that is directly attached to the bromine atom, or the one that's closest to the bromine atom. So in this particular case, let's start up here. We're looking at this carbon, right, in this case. And then in this case, we're looking at this carbon. And then down here, we'll be looking at this carbon, which is a part of the phenyl ring, okay? So what we're looking for effectively is if the bromine is going to leave as a bromide ion, right, then what's going to happen is that it's going to take all the electrons with it, right? That's how it's going to end up leaving as a bromide ion, right? So if there is some kind of a heterolytic fission there, right? And so we have that leaving then with all the electrons, and so we end up having the bromide ion, right? So that's what needs to happen. In all these cases, that's what's going to need to happen, okay? So what we need to figure out then is in which of these cases, right, is the carbon positive or most positive so that the bromine can take all the electrons onto itself, right? Because that's the case in which the bromine would take all the electrons onto itself. So let's start up here, right? If we look at this carbon here, that's what the bromine is bonded to. This carbon is attached to this carbon, which is attached to this electron withdrawing group, which is a carbonyl group, which is also attached to a phenyl ring. So what you're going to find is that the electrons are going to be pulled this way in towards the ring. And so the net effect is that this is going to have a partial positive charge, and that's going to leave the bromine with a partial negative charge. And so it will be easy for it to take the electrons onto itself. So that's how it's going to work, right? But let's rank the electron withdrawing power of all of these groups is what we have to do, right? So this is going to withdraw to a great extent, right? And the bromine is here. So that's going to withdraw to a great extent, but to an even greater extent is this carbonyl carbon that's directly attached to the bromine, right? So this one is gonna there's nothing in between it, right? There are no other groups on it to shield the bromine from that from that whatever the charge differential will be. But in this case, there's nothing in between. So the bromine is directly attached to this withdrawing group. So there's going to be a strong positive charge here, right? So it would be easier to remove it from this than it would be from here. And so we'll say Y would be easier to remove from than X. And then in this case, let's look at this. We have our phenyl ring, and that's where the bromine is attached directly to this phenyl ring, which we know is electron withdrawing, right? So it's gonna make this carbon super positive, really positive. And so the bromine is gonna then take the electrons onto itself and leave as a bromide. And it's actually easiest to do it in this case out of all of them, simply because the carbon is in that phenyl ring, okay? And it's gonna be, the electrons are gonna be pulled away from it, from the ring, by the ring, okay? So this one will be easiest, which is Z. So Z is gonna be easiest, which is greater than Y, and it's gonna be, Y is gonna be easier than X, okay? So that's our answer here. And so that's, what did we say? We said decrease in E. So which one is easiest to remove? What did we say? What was our ordering, guys? We said it would be, C here, right? Let's see, is it C what we got? So we said, what would be the easiest one? So we have the bromine attached directly to a carbonyl here, right? And the carbonyl is withdrawing in addition to the phenyl ring. So that's a combined effect of the phenyl ring and the carbonyl. And then in this case, we just have the carbonyl and the phenyl all the way down here. And the carbon is all, that the bromine is attached to is all the way here. So whatever the case is, this is gonna be the least one, right? This is gonna be the hardest to remove it from. And this one is just only directly attached to the phenyl ring, right? That's the carbon that the bromine is attached to. So actually your ranking will then be Y, because you have the combined effect of these two being electron withdrawing. So it will be Y is greater than Z, which has only the phenyl ring withdrawing, and that's going to be greater than X, which has the withdrawing groups far away from the bromine, okay? So this is our order. So our order is Y, Z, X. So that would be Y, Z, X, right? So that would be D. Okay? So that's our answer here. So 9 is D. So moving right along to question 10. Question 10 refers to the following compounds, which is A is shown here, which looks to be, what is that? This looks to be a ketone, right? There's a C double bond O, R group on that side and an R group on this side. This looks to be an amide, right? We see that C double bond O. We see a NH there as well. So that looks like an amide. This looks like an aldehyde. We see a C double bond O. We see a H. And we see a R group. And then this one here looks like an ester, right? You see that? COO. So we see that there's like a C double bond O, and then there's a R group on either side, right? Okay, so match each item below with one of the options above, each of which may be used once, more than once, or not at all. So 10, they're asking which one is the aldehyde, and what did you say the aldehyde was? The aldehyde was C, right? And 11 is asking about the ester, and we said that D was the ester. So D is our answer for 11, okay? All right, so moving right along to question 12. Question 10 says, which of the following is not oxidized by potassium permanganate that's acidified, right? So we know that alkenes can be oxidized, right? And those would give us a diol, right? So that would form a diol when oxidized. So we know that this is going to be oxidized. A ketone, no, ketones can't be oxidized because remember what oxidation is? Oxidation is the removal of hydrogen, right? And the addition of oxygen. And so there are no oxidizable hydrogens here. And so B is the answer here. We can't oxidize ketones. We can oxidize aldehydes and we can oxidize alcohols, right? But we can't oxidize ketones. And so our answer here is B for 12, okay? All right, so moving right along to 13. 13 says which pair of compounds is formed when benzene and methyl benzene undergo nitration, right? So we're nitrating benzene and we're also nitrating methyl benzene, okay? All right. And so let's see here. So we have this nitrogen looks to be in the 1 carbon position, which would be fine for the nitration of benzene. So let's look at methyl benzene. In methyl benzene, this is our 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, right? Now we know that the methyl group is 2,4 directing, right? So when methyl benzene undergoes nitration, the nitrate group should be on the either the 2nd carbon or the 4th carbon, and we see that that's not the case here, and so we have to rule out A, right? Let's look at B now. B is saying that we would get, what is this? 1, 2, 3, 4. We'd get a 2,4 nitrobenzene, and that's not entirely accurate as to what we would see. And in this case, it's saying that we'd get 2, 4, 6. And this isn't entirely accurate either, right? So let's look at this one now. This one is saying that we would get a 2 nitrate groups being added. 1, 1. So this is our 1, 3 kind of a situation. Not entirely accurate either. And in this case, what do we have? We have a 3, 4. We have a 3, 5 situation, and that's not correct. Because as we said, the methyl group is 2, 4 directing. So the nitrogen, the nitrate group that gets added onto the methyl benzene has to be either the 2 position or the 4 position. And so this is the only one that kind of reflects that. 1, 2, 3, 4. There's one in the 4 position, and then we have this singular one by itself. So out of all of these selections, this is the most accurate representation. And so our answer is D. Okay, but the key thing to remember for these kinds of questions is, okay, if I have methyl benzene and I'm gonna try to put on some nitrate groups, where are they gonna go? It has to end up in the 2, 4 direction. It's because it's 2, 4 directing. It has to end up on either the 2nd or the 4th carbon, right? And so this is the only one that shows that. In fact, it shows it being on the 4th carbon. So this is what 1, 2, 3, 4. And so we know that this is our answer here. Okay, so this is the answer for 13. So moving along to 14. 14 says ethanoic acid, which is an acid. It turns blue litmus red, which is what we expect of acids, right? But ethanol does not, because ethanoic acid has a polar OH bond, but ethanol does not. That's not the reason why. Has a higher pKa value than ethanol. That's not true, right? Because the lower the pKa is, the stronger the acid. And we know that ethanoic acid is a stronger acid than ethanol, and so its pKa would actually be lower. So this is not even an accurate statement at all, right? But we do know it's a stronger acid than ethanol, and we know that acids are the things that turn blue litmus red. And so this is our reasoning, right, behind why ethanoic acid turns blue litmus red, but ethanol does not. It's because ethanoic acid is a stronger acid than ethanol. So our answer for 14 then is C. Okay. So moving along to 15 now. 15 says, which of the following statements about aminoethanoic acid is not true? So what's not true about aminoethanoic acid, which is an amino acid, right? So let's see. What's not true? Its aqueous solution has a pH of 7. That's true because it's neutral, right? Amino acids are neutral in aqueous solution. They have a high melting point. That's true because they're crystalline solids in nature, so they'll have a high melting point. Is it soluble in base only? That's not true. It's not gonna be only soluble in base because it has an acidic portion as well as a basic portion, so it will be soluble in both, right? So this is what this says. It is soluble in both acid and base, and that's true. So what's not true is the statement that it's only soluble in base only. That's not true, okay? So C is not true. So 15 is the C is the answer for 15, okay? All right, so moving right along to 16. 16 says in an iron determination, a student obtains a mean value of 35.50% for the iron content and a standard deviation of 0.01. right? So what the student got was 35.50 for their mean, and the standard deviation is just plus or minus 0.01, right? The actual value, though, for the percentage of iron in the sample is known to be 39.45. So they're asking, in terms of precision and accuracy, which option best describes the student result? Is there high accuracy and high precision? No, there's high precision, but there's not high accuracy, because you can see this is the true value, and the student was way off. They got 35.50. That's very far off from what the true value is, right? But the standard deviation is pretty tight. So we see that there's high precision because the student was able to reproduce their measurements very well, so that there's this small standard deviation. So it's high precision is in the readings, but not high accuracy. We don't have high accuracy, so we can strike out this one as well. And we have high precision, so we can strike out that. Low accuracy, that's correct. And we have high precision. So C is our answer. Again, remember, it's low accuracy because it's not the student's reading is not close to the actual one. So it's low accuracy. And because our standard deviation is fairly small, we know that we have high precision. The student had high precision in the measurements, okay? So the answer for 16 is C. So moving along to 17 now. 17 says, which of the following is not a characteristic of primary standards used in titrimetric analysis? So what are some characteristics of primary standards? Is it that it has to have high purity? That's true. Does it have to be stable in air? That's true. Does it have to be deliquescent? That's not true. Deliquescent is a property of salts where they dissolve in water to form liquid, and that's not necessarily true. But what's true is that they have to be soluble, right? That's true. So they have to be soluble. So that's true. But deliquescent is not a requirement of primary standard, and so this is not required, and so our answer here is C. Okay, so 17 is C. And so moving right along to 18 now. 18 says, which pair of titrations is methyl orange, which has an indicator range of 2.9 to 4.6, best suited for? All right, so if we have a strong acid, that would have like a low pH of, say, maybe 2, and we add a strong base to it that has a pH of upwards of anywhere from 10 upwards, right? And so on. And if we have a strong acid, again, 2, and a weak base that we're adding to that, weak bases of low pHs in the region of maybe, say, 8, right? 8 to 9. If we titrate these pairs, can we use an indicator that's in this range? Of course, because it would overlap, right? So our answer here is A. It wouldn't necessarily work as well for these other ones, right? If we have a strong base and a weak acid is around what, 5, right? And then the strong base is high up at like 10. So we kind of realize that we skip over this range, right? You see that? So we know that it wouldn't work in this case for that pair. And if we have a strong acid and a strong base, it would work for this pair, but it wouldn't work for a weak acid, which is like 5, and a weak base, which is like 8, right? We skip over this indicator range completely. So we couldn't use it for this, and we couldn't use it for this. Could we use it for this? Strong acid, weak base, that would be what? pH 2. Weak base would be pH, we would say maybe like pH, what did we say for weak base again? Around 8, right? We could use it for this first one, but could we use it for this last one? Strong base would have what we said, 10, and we said weak acid would have like 5. Again, we skip over it for this pair, so we can't use it for this either. The only one where it works for both the first pair and the second pair is A, right? Because it overlaps perfectly with this indicator range of methyl orange, and so we will see our endpoint, okay? So 18A, all right. So we're moving along to 19 now. So 19 says 25.0 cm cube of an aqueous iron 2 salt is acidified with an equal volume of dilute sulfuric acid and titrated against 0.02 mole per dm cube of potassium manganate 7 solution. The endpoint is 30 cm cube, right? So because we're titrating the iron, right, the acidified iron, against potassium manganate solution, the amount of manganate at the endpoint that we use in terms of volume was 30, right? So let's just write that here, 30.0 cm cubed, right? That's how much volume of that we end up using at the end point, right? That's what the question tells us. So let's look at this equation that they give us now. They're asking us to find the correct concentration of iron ions in mole per dm cube that was in that sample, right? So when we look at the balance equation, we can come up with our mole ratios as to how many moles of iron is going to be reacting with the potassium manganate, right? And we see that there's a 5-to-1 mole ratio, right? So the next thing that we have to do is find how many moles of potassium manganate were used up by the time we got to the end point. So they told us that there are 30 cm cubes of it that got used up, right? And so we need to find the number of moles that were actually used up. We know in theory what the mole ratio is. It's a 5-to-1 iron to KMnO4. But we need to know how many moles are actually used to neutralize the iron. And so let's come over here, and we know that moles is equal to concentration times volume. And so concentration will be equal to moles divided by volume, right? And so we can find out the number of moles of MnO4 that were used by multiplying its concentration times volume. And so we could do 0.02. So that's concentration times volume was 30, right? cm cube. And so we know that that would give us what? If that would give us 0.6, right? 0.6 moles of KMnO4. And so we know there's a 5-to-1 mole ratio. So 0.6 times 5 would be 3 moles. So there are 3 moles of iron 2 ions that we started out with, and we use 0.6 moles of KMnO4 to completely neutralize it, right? But we want to actually find the concentration of the iron ions. So what did we do? We would have to do concentration is equal to moles, which is 0.02 times 30. So this is the number of moles of KMnO4, and then we multiply that by 5, right? Because there's a 5-to-1 ratio, and then we divide that now by concentration is moles divided by volume, and they told us that it was a 25 cm cube volume of iron salt that we use. So we divide by that volume that's specific to iron salt, and when we do that, we see that these cancel, and so we're going to end up with 0.02 times 30 times 5 divided by 25. And that's this one here, right? So this represents the concentration of iron ions in mole per dm cube. So remember now, to approach this kind of question, look at your balanced equation first of all, pull out your mole ratios of the species that you're titrating, right? Then you find the number of moles of what you're titrating against that were used, and then by extension, you'll be able to find the moles of how much of your analyte you had, right? Which in this case is iron. So we had 3 moles of that, and then we can find concentration by dividing by the volume of this that we use, which was 25, okay? So that gives us B for 19. So moving right along now to 20. 20 says treatment of an 8-gram sample containing a lead ore with excess sulfuric acid yields 4.75 grams of lead sulfate, right? So we have a sample that contains lead ore. We're going to add sulfuric acid to it, excess, and we're going to get 4.75 grams of lead 2 sulfate. The correct expression for the percentage of lead in the sample, right? So how much lead was in that original sample is, all right. So here's how we're going to approach this one now. So we know what mass of the sample we started with. The sample containing lead we started with, that was 8, right? And in the end, we know that we got 4.75 grams of a lead 2 sulfate sample. So from a mass standpoint, because we're trying to find percentages of lead in the sample, our first step is to say, okay, from a mass standpoint, In the end, we had 4.78 grams of the 8 that we started with. So we do 4.75 over 8. So that accounts for this mass that we got, right? And then now, because we want to find out how much lead is in it, how much lead was in the original sample, then we have to say, okay, what's the mass of lead? The mass of lead in lead 2 sulfate is 207, and the total mass of the lead sulfate is 303. So the fraction of lead that's in the lead sulfate is 207 divided by 303. And finally, for the percentage conversion, we multiply by 100, okay? So there are 3 parts to this thing. How much mass of the original sample do you have at the end, which is captured here? And how much of that whole thing that you have at the end in terms of the molar mass, how much of that is attributable to lead, right? So we know that the molar mass of lead is 207. So we divide that by 303, which is the molar mass of the lead 2 sulfate, okay? And then finally, we multiply that by 100 since we're trying to find the percentage. And so we have to look for this among our answers, right? So let's look for this. 207 over 303 times 4.75 over 8. So that would be C, right? So our answer for 20 is C. Okay, so moving right along to 21. 21 says sintered glass crucibles are used in gravimetric analysis because they have negligible weight. That's not the reason why. They can tolerate high temperatures. That's actually why, right? Whenever we want to heat to a high temperature to drive off the water or whatever the case may be when we're doing our gravimetric analysis, right? We're gonna have to heat, whenever we have to heat to high temperatures, we're gonna use that sintered glass crucibles, okay? So 21 is B. That's why we use them in gravimetric analysis, because they can tolerate high temperatures. So 21 is B. Moving along to 22, 22 says, in the determination of the purity of a sample of magnesium carbonate, which we know is a weak base, right? By back titration method, which of the following statements is incorrect? So you know that in back titration, you're using an excess of one of your reagents to figure out, right, what the concentration of your unknown is, right? So phenolphthalein or methyl orange are suitable indicators. That could be true, right? Depending on the base that we're using or the acid that we're using, that could be true. The amount of excess acid remaining is determined by titration with a standard alkali. That would be the case, right? We would be using a standard alkali to figure out how much was in excess, or how much was unreacted. So that's correct. The sample is reacted with excess alkali. No, this is not true, and here's why it's not true. If magnesium carbonate is a weak base, right, and you're doing back titration, you can't titrate a base with a base, right? You have to use an acid. So the sample is not gonna be reacted with excess alkali because it itself is an alkali, right? So this is incorrect. You'd actually be reacting the sample with excess acid, right? So C is incorrect here. Unreacted magnesium carbonate is filtered off and weighed. That is true. So we would do that in gravimetric and in back titration, okay? But this part is not true. You can't titrate, or you can't react a base with a base. You'd have to use an acid, right? Okay, so 22 is C. So moving along now to 23. 23 says, which of the following substances would be produced by fractionating a 20% solution of nitric acid in water? Would it be azeotrope nitric acid? No. Would it be water and nitric acid? That's not true. Would it be nitric acid only? Yes, and we'd get off only nitric acid when we do that kind of fractionation, okay? So the answer for 23 is C. And so moving along to 24, 24 shows us the structure of caesalpinene, right? And so let's look at it. Let's look at the structure here. What are our functional groups that we can see? We see there's a carbonyl here. What else do we see? What else do we see here? We see that there are a lot of ring structures here. We see that there's a OH group here. There's a carbonyl here. right? And then we just have a bunch of like methyl groups, and this looks like a ketone of some sort. Or this looks like an ester rather. Okay, so there's some sterile functional groups in here. So the compound C-alpine exhibits absorption at wave numbers 3,400 inverse centimeters and 1,750 inverse centimeters in the IR spectrum, right? So this is a question about IR spectroscopy. And so it's saying which functional groups are responsible for these absorptions. So we know that the OH group is going to be picked up at around 3,400 inverse centimeters. So that would be an OH group. And then 1750 is our carbonyl group that's here, right? And so we have OH and C11O. And so that our answer here is going to be A. Okay, so for a question like this, you would just consult your data tablet, your data booklet, and then just see what would correspond to these respective wave numbers, and you'd come up with OH and the carbonyl, okay? So the answer for 24 is A. So moving along now, question 25 says the use of IR spectroscopy in identifying structures of organic molecules is limited because, like, why would it be limited? What are some limitations of infrared spectroscopy? Is it limited because it helps to determine the presence or absence of some functional group? No, that's actually why we use it, right? So this is not a limitation of it. Would it be limited when the spectrum of molecules, if the spectrum of molecules are complex, where some absorption frequencies are superimposed, means that they're on top of each other, and we can't accurately distinguish between them? That's correct. So this is correct here. So this is a limitation of IR, right? You have some molecules that their spectrum are so complex, right? And functional groups are on top of each other, and you can't really tell, right? Because the absorption frequencies overlap. So that's B here. So the answer here is B, and that this is a limitation of IR spectroscopy, okay? So let's look at 26. 26 refers to the following gas liquid chromatogram, right? So we see that we have our recorder response here, and then we have the time of injection here, right? And the question is asking, based on the chromatogram, which of the liquids is present in the largest quantity? So when you look at a gas liquid chromatogram, the liquid that's present in the largest quantity is going to be the one that has the largest area under the curve, right? So under the peak. So when we look at all of these peaks, the area under the peak can be simplified to that of a triangle. And so if we were to find this one, the area under this one would have half base times height. And then this one is the same, half base times height, right? And so ultimately, C is going to have a greater area than any of the others. And so because it has a greater area underneath this peak, the liquid that's present in the largest quantity will be in C, right? So our answer for 26 then is C. So remember now, whenever we're talking about quantity of liquid, we're looking at the area under the peak, okay? All right, so C is our answer here. So 27 is about atomic nuclei pairs, and which of them both have a nuclear spin, and our answer here is C. I don't think that this has carried over to the new syllabus. So this is from NMR spectroscopy, which we don't cover in this day's Cape Chemistry Unit 2. But the answer would be C, okay, for 27. Okay. So we're moving along to 28 now. 28 says, which of the following equations governs the determination of an unknown compound X in a solution by UVV spectroscopy? So whenever we think about UVVs and we think about equations as it relates to UVVs, we're always going to be thinking about Beer-Lambert's law, right? And of all these equations here, this is the one that captures Beer-Lambert's law, where it's a log to the base 10 of the transmission of light in the pure solvent over the transmission in the reference cell or in the test cell, right? So this is for transmission in our test cell, this is for transmission in our pure solvent, and that's equal to ECl, right? And that's Beer-Lambert's law. So A is gonna be our answer in here for 28, okay? This one is, the eyes are flipped, and so this wouldn't be correct. And this isn't Beer-Lambert's law, and this isn't Beer-Lambert's law either. So our answer is A because it's a log of I naught over I is equal to ECl, right? So 28 is A. And so moving along to 29, 29 is which of the following are all examples of commonly used stationary phases in chromatography? So commonly used stationary phases that we use silica gel, alumina, and cellulose. These are the most common ones that we'll come about, right? So remember, our stationary phase is the one that doesn't move, right? That you typically have your analyte binding to different extents. And so these are the ones that we commonly use for our stationary phases, right? In chromatography, a silica gel or alumina, or we use cellulose, right? So those are the ones that we use for stationary phases in chromatography most commonly. So 29 is B. So moving along to 30, 30 says that a solution of 5 grams of an organic compound X in 200 centimeter cube of water is shaken with 100 centimeter cube of chloroform, right? Then when we do that shaking, we're gonna find that there's 1.3 grams of acid remaining in the aqueous solution at equilibrium. And then they're asking us now to find the partition coefficient of X between water and chloroform, right? So this is a solvent extraction situation where, you know, there's some of the components are gonna go into the aqueous phase as they're telling us here, and some are gonna go in the organic phase. And so the partition coefficient then we can say is the concentration of X in the chloroform phase, which is our organic phase, over the concentration of X in our aqueous phase, which is water, right? So in the organic phase, there's gonna be what? 5 minus 1.3 minus whatever is in our aqueous phase. So 5 minus 1.3 is gonna be 3.7. And we divide that by the volume of the organic phase. So it's 100 cm cube of chloroform. So we divide that by that. So this is just mass divided by volume for that concentration at equilibrium in the organic phase, which is chloroform. And then under here now, we have the mass that they told us was remaining in the aqueous phase over the volume of the aqueous phase, which was 200 cm cube of water, right? So this is our expression for KD. So we have to look for something that mirrors this in our answers, okay? And when we look among our answers, this is the only one. This is the one that captures all of that, right? And so we see that here, there's 3.7 divided by 100. So that's 3.7 times 10 to the minus 2 effectively. And then down here, if we divide through the 1.3 by 2, we end up with, if we multiply by 10, we end up with 13. Divide that by 2, we end up with 6.5. And so we get 6.5 times 10 to the negative 3 for the bottom portion, okay? So this is our answer here for this one. So 30 is B, okay? All right, so moving along now to 31. 31 says, in the conversion of bauxite to pure aluminum oxide, what is the compound obtained after filtering and adding carbon dioxide to impure bauxite? So impure bauxite is what? That's Al2O3, right? So when we add carbon dioxide to this, we're gonna get aluminum hydroxide, right? This one here, just a neutral aluminum hydroxide compound. So our answer for 31 is gonna be A, okay? So moving along to 32 now. 32 says crude oil is separated into petroleum products by use of fractional distillation. Which fractions would be obtained between 200 degrees C and then between 275 and 375 respectively? Okay. Is this where bitumen is found at this temperature? No. So we can rule out A. Diesel and kerosene. These aren't the temperatures that correspond to those either in fractional distillation. So we can rule out B. Naphtha. Naphtha would be within this region, so that would be correct, but the refinery gas wouldn't be at this high temperature. So this part is incorrect of this pair. And so it's not C, and so that leaves us with D. Okay? So our answer for 32 is D, and that's really just matching temperatures to fractions, okay, from crude oil's fractional distillation. So 32 is D. So moving along now to 33. 33 says purified N2 gas and H2 gas are reacted together to form ammonia as shown below. Right? And so we see that we have a mole of nitrogen gas reacting with 3 moles of hydrogen gas. There's a catalyst that's present. It's in equilibrium, right? So we see it's forward and backward arrows, an equilibrium reaction, and we see that we get 2 moles of ammonia gas, right? And we also see that the forward reaction is exothermic since heat energy is given off, right? As seen by this negative delta H, okay? So based on the Chatelier's principle, which combination of pressure and temperature would give the highest yield of ammonia? So the forward reaction is what produces ammonia. So we have to think what would favor the forward reaction based on the Chatelier's principle, right? So we look at this equation, we see that there are 1 mole and 3 moles. There are 4 moles of molecules on the reactant side. And there are 2 moles over here, right? And so if we increase the pressure of the system, it's gonna want to shift to the side where there are fewer molecules. And so if we have a high pressure, we're gonna favor the forward reaction based on the Chatelier's principle, right? So remember now, when you have a high pressure system, when you put high pressure in the system, it's gonna want to go where there are fewer molecules to relieve that pressure, right? That's what the Chatelier's principle says. And from the standpoint of it being an exothermic reaction, right? It means that it gives off heat, right? If we suddenly drop the temperature of this reaction mixture, then what's gonna happen? The reaction is gonna want to shift to the right so it can generate more heat, right? So if we decrease the temperature, if we are at low temperatures and high pressure, we will get the highest yield of ammonia since the ammonia production is related to the forward reaction, okay? So we increase the pressure, the equilibrium is gonna shift to the right. If we decrease the temperature, then the equilibrium is gonna shift to the right, right? And so our answer is low temperature and high pressure, okay? Low temperature, high pressure, so that's B, okay? 33 is B. So moving along to 34, 34 says ethanol formed by fermentation will destroy the enzyme producing yeast, right? So when we're doing fermentation, when we're converting glucose to ethanol, there's a certain point at which we have to stop, right? Before the ethanol poisons the yeast, right? And so what is the lowest percentage of alcohol at which that destruction starts to occur? It occurs if you're over 15% alcohol, then you're completely done. Like it's not gonna go any further, right? So 13%, yeah, around there is where you start having the poisoning of the enzyme. So this is around where you'd have to kind of stop, right? So 34 is B. And so we are moving along to 35 now. 35 says that the oxygen used in the contact process must be dust-free to avoid poisoning the vanadium 5 oxide catalyst, right? Which reaction will be affected if dust is present? So the step that includes the vanadium 5 oxide as a catalyst is the sulfur dioxide conversion into sulfur trioxide, right? So we have to look for that equation among these ones. It's not this one. It's not this one. It would be this one, right? Where we're going from sulfur dioxide to sulfur trioxide. This is the step that uses that vanadium 4 oxide. And so this is the one that would be affected, right? If we have dust in our mixture, it would poison the vanadium pentoxide catalyst and we wouldn't be able to get this step done, okay? So this is the affected step. So that's C. Our answer for 35 is C. Okay? Excuse me. So moving along to 36. 36 says, what is the purpose of green chemistry? What is this whole, what is all the rage about green chemistry? Is it about removing waste from industrial reactions? Not particularly. Is it about designing chemical products that maximize profits? No, it's not a profit-making thing. It's about inventing technologies that will promote recycling of products? Not entirely. Is it about designing safer chemical products and processes that reduce or eliminate the use of and generation of hazardous substances? Yes, this is the all-encompassing, definition of what green chemistry is all about. So our answer for 36 then is gonna be D. Okay. All right, so 36 is D. Moving right along to 37. 37 says a polluted river near a paint factory is tested with acidified potassium iodide and a bright yellow precipitate is observed. Which of the following pollutant is likely present, right? So we know that whenever we see that yellow precipitate, whenever we have potassium iodide in the mix, whenever we have Ki in the mix, right? And we're gonna get that bright yellow precipitate, it means that there is some lead iodide that's being formed, okay? So it's lead iodide that's being formed in that case. And so this then signifies the presence of which pollutant? It would be a lead that's present, okay? So 37 there is D. Okay? All right, 37 is D. And we are moving along to 38. 38 says a substance formed in combustion engines of vehicles, which may lead to the formation of acid rain is. So we know that acid rain is formed from the oxides of sulfur or the oxides of nitrogen. So we're looking for an oxide of nitrogen or sulfur here because that's what would form acid rain, okay? So it's not going to be A. B, we see that B is an oxide of nitrogen, so that would be it, right? Neither of these wouldn't form acid rain. It's only oxides of nitrogen or oxides of sulfur. So 38 is B. Moving right along to 39. 39 says it's estimated that one chlorine radical, right? A single chlorine radical will break down 10,000 ozone molecules. Which feature of chlorine radicals may account for this, right? And the feature here of this chlorine radical is that it regenerates itself, right, by reacting with ozone. And so one of them can, regenerate itself as it reacts with ozone. And so you can continue breaking down more and more ozone molecules, okay? So that's that regeneration ability of that chlorine radical is what makes it able to break down that many ozone molecules per one radical, okay? So the answer here is A for 39. So moving along to 40, 40 says, which of the following cannot be used to control atmospheric pollution? Does using cleaner fuels in industrial plants make for a better control of atmospheric pollution? Yes, this is true. Catalytic converters, yes, that helps to minimize pollution or control it to a certain extent. Does decreasing vegetation in urban areas help? No, because we're cutting down the plants. That can't be good for us, right? So that's not going to help in controlling atmospheric pollutions. If we use chemical scrubbers, those could help, right? But this is the one that cannot be used to control. And that's what the question is asking us about. We can't decrease vegetation in urban areas as a means of controlling atmospheric pollution, okay? So 40 is C. Okay? So moving along to 41 now. 41 says water can be purified by all of the following except can we purify water by desalination? Yes. Reverse osmosis? Yes. Distillation? Yes. Can we use sublimation? No. We can't use sublimation. That's not a purification method, right? That's kind of a change of state on how we would go from solid to gas or gas to solid. That's not going to help us purify water, okay? All right. So 41 is D, okay? We can't use sublimation to purify water. So moving along to 42 now. 42 says the ozone layer is a thick blanket over the Earth's surface. It prevents UV radiation from entering the Earth's atmosphere. Where is the ozone layer located? Where exactly? The ozone layer is located in the stratosphere, right? So our answer for 42 is going to be B. That's where the ozone layer is located. It's in the stratosphere. Okay, so moving on to 43 now. 43 says, which property of aluminum make it suitable for constructing airplanes? Well, it's low density, it's light, that's good, right? We don't want the planes to be too heavy. So the fact that it's low density, aluminum is low density, we can use it. There's an impermeable oxide layer over the aluminum, which makes it able to withstand all kind of chemical you know, whatever it is that's going on up there in the air. So this is good for us. Conduct electricity? No, guys, we don't want that. We don't want that in our airplane. So that's not a property of aluminum that makes it particularly useful for constructing airplanes, because it has a low density, and it's because it has an impermeable oxide layer where we can use it in constructing airplanes, okay? So that's 1 and 2, and so that would be A. So the answer for 43 is A, okay? So let's go down to 44 now. 44 says that the term residence time for gases in the atmosphere refers to the length of time the gas takes to move from the Earth's surface to the upper regions. That's not true. Is it the length of time that the gas remains in the atmosphere until it is removed in a sink? Yes, that's what we mean by residence time, right? How long does it stay, just linger in the atmosphere until it's removed by a sink? That's our residence time for that gas, okay, in the atmosphere. So 44 is B. And so moving on to 45, 45 says, which of the following chemicals form a non-toxic substance when it reacts with nitrogen monoxide? And that is carbon monoxide, right? So when carbon monoxide reacts with nitrogen monoxide, it's going to form nitrogen, which you know is not toxic, and it's going to form carbon dioxide, which you know is not toxic, right? So this is one of those reactions from the catalytic converter. And so that's what would happen, right? Non-toxic substance is the key word. And then we have nitrogen monoxide. And so if any of these other ones react with it, it's going to be problems, right? But if carbon monoxide reacts with nitrogen monoxide, we're going to get some non-toxic substances like nitrogen gas and carbon dioxide, okay? And with that, we've come to the end of this test. I hope that this was helpful for you guys. Definitely drop a like down below, like the video, drop a comment and let me know if this was helpful for you. Please subscribe to the channel and share this with a friend. And I'm wishing you the very best in your exams, and I'll see you in the next video.